What I'm going to be talking to you today about is stuff around the question that I think we're all wondering, which is how can AI and machine learning really help us solve really challenging problems in society? Not just computer science problems, but how will it impact many, many things in the world? And I'm going to be presenting the work of many people at Google, so it's not all purely my work. I'm telling you about work that I think is interesting and exciting. The reason we're here, though, is there's a lot of excitement about machine learning in the world, and it's really caused lots and lots of people to start to enter the field, to want to do research in the field, to want to apply machine learning to their problem. So much so, in fact, that the number of machine learning papers posted on Archive, which is a preprint hosting service, is growing at faster than the old Moore's Law exponential growth rate of computational power that we got so nice and used to for 40 years, but has now slowed down. So we've replaced the growth in computational power for traditional computers with lots and lots of people thinking of great ideas and posting them on the research community's website. And one of the exciting areas of machine learning is deep learning, which is really just a rebranding of some ideas that have been around for quite some time. There was actually a lot of excitement about neural networks in the 80s and 90s as kind of a really interesting abstraction that would enable us to sort of model interesting pattern recognition systems that could be hierarchical. We could learn patterns of patterns, that we could build up these features automatically through learning algorithms that can learn from very raw forms of data. And in the 80s and 90s, they proved to be able to do really interesting things with toy-sized problems. In fact, in 1990, I did a senior thesis on parallel training of neural networks, because I felt like they were the right abstraction for a lot of different kinds of problems, but they just couldn't scale up to real-sized problems. So I felt like if I could get the 64 processor machine and the computer science department I was in, to train neural networks in parallel, we could get 60x speed up. It would be amazing. We could train gigantic models. Turns out we needed like 1 million times more compute, not 60 times more compute. So we had to wait a while. And around 2008, 2009, 2010, we suddenly started to have computational devices that would actually give us enough computational power to apply neural networks to real problems. So I think that's one of the really exciting things that has started to happen, is now neural networks and deep learning are really showing their promise. So neural networks can learn essentially functions from data, input-output relationships. And this is not like y equals x squared kinds of functions. These are actually quite complicated functions. So for example, there's been a lot of improvement in computer vision. A computer vision model can take in the raw pixels of an image and give you, for example, a category of what is the kind of dominant object in that image, and not just for sort of high-level categories, but even very precise things like particular kinds of monkeys. For audio, we can take in raw audio waveforms and, for example, produce transcripts of what is being said. This is essentially an end-to-end approach to learning speech recognition models, which is an important sub-area of computer science that has been worked on for many years, but neural networks are now showing the best speech recognition results and really making dramatic improvements there. They can take in language, one word at a time in English, hello, how are you, and be trained to spit out the corresponding meaning sentence in another language. Bonjour, comment allez-vous? I apologize for my French accent. They can even do more interesting things than just give you a categorical output for an image. They can take in the pixels of an image and actually produce a small, short, simple sentence that describes that image. A blue and yellow train traveling down the tracks. So that's actually a pretty complicated task. Like, the model has to understand enough from the pixels that this is a train, that it's blue and yellow, that it sits on tracks. And if you'd asked me 3 or 4 years ago if computers could do that anytime soon, I would have said, that seems pretty hard. I'm not really sure. But we've now made a lot of progress, and we actually, as of about 3 years ago, have models that can do this for fairly simplistic sentences. Just to give you a sense of the improvement over the last few years, largely due to computation and also a bunch of better ideas in the last few years and sort of more computation, in 2011, Stanford runs an ImageNet challenge every year to see how well computer models can take an image and produce one of 1,000 category labels How accurately can they do that for images that the model has never seen before during training? And in 2011, the year before people started using neural networks, the winning entry was 26% error, which is not particularly great. And we know that human error rate on this task is about 5%. And in 2016, we're now at 3% error for computing systems. And so that dramatic improvement really has fundamental consequences for lots and lots of things. Right? Computers basically didn't used to be able to see, now they can see. That has ramifications for many, many things. So the way I'm going to structure the rest of the talk is in 2008, the US National Academy of Engineering got together a bunch of people from many different fields, and really this commission looked at what are the grand engineering challenges that these science and engineering and computer science communities should really be thinking about for the 21st century. I guess they waited until 2008, so we only have 92 years. They lost us 8 years by not convening the panel soon enough. But they came up with this list of 14 different topics. And I think if you look at this, it's a nice broad spectrum of things that are really important in society. If we actually solved all these problems or made a lot of progress on them, the world would be healthier, people would know more, we'd be able to make scientific discoveries faster, and the world wouldn't be heating up quite so much. So these are great challenges. I actually think machine learning is going to help us in solving all of these problems. We have work at Google in our research organization for all the ones that I listed in red. And I'm going to be talking to you about the ones that are in boldface. OK, so one of them is restore and improve urban infrastructure. And one of the things that we're on the cusp of is autonomous vehicles, right? We're very close to actually having viable commercial deployments of autonomous vehicles. And in part, this is largely enabled by the fact that deep learning and machine computer vision now work, right? Basically, these vehicles have to take in lots and lots of sensor data. They have many cameras around the car. They have these LiDAR things that spin around to give you sort of 3D depth point clouds. They have radar information. And fusing all that together and building a model of the world around the car so that it can understand what other objects exist around it, which ones are pedestrians and are likely to move, which ones are light posts and are not going to move, which ones are other cars and what their likely behavior is going to be. That's key to making a car that can actually operate safely and get you from A to B and in a way that respects all the traffic laws and does so safely. And to give you a sense of where we are in this, Waymo, Google's parent company, Alphabet, has a self-driving car subsidiary called Waymo that we collaborate with quite closely in the research organization. In Phoenix, Arizona, in early January 2018, Waymo is actually running a trial with about 100 cars in Arizona with real passengers in the back seat and no safety drivers in the front seat. So this is not some distant, far-off thing. This is actually cars driving around Phoenix, Arizona with passengers in the back seat with no safety driver there ready to take over at a moment's notice. And so that's, I think, a sign that this is a pretty close technology. Another area that I think is going to be improved is robotics. The fact that computer vision now works means that we can actually consider making robots that can learn end-to-end from their perceptual inputs to performing different kinds of actions. So if we can play the video, maybe we'll just play. I don't know how to play the video. There we go. There's a mysterious mouse. So one of the great things about robotics is you can actually have robots experiment and sort of do self-experimentation to see how well they can do different things. And grasping turns out to be a really nice aspect because you can actually tell if you succeeded in picking something up or not. Because your gripper doesn't close all the way and there's a thing in your hand at that point. And the other nice thing about robotics is you can actually pool the experience of many robots trying to accomplish the same task and then train on that data. If we can skip to the next slide. Or maybe I can. If you go to the right-hand white column. There you go. So one of the things about that is we've been able to make significant improvements in grasping success rate. So before we started this work of having sort of a parallel robotics lab attempting to grasp things, the grasp rate on a particular task was 65%. So 65% of the time you want to pick something up, you're able to successfully pick it up. This is for an unseen kind of object you've never sort of grasped before. And in 2016, our robotics research group published this paper that sort of combined together a bunch of robotic experimentation and was able to achieve a 78% grasping success rate. And if you fast forward 2 more years, continued improvements to that system and the use of reinforcement learning rather than sort of just purely supervised learning, we're now at a 96% grasping success rate for unseen objects, same task. So we've gone from 65% to 96% success. And that has a pretty dramatic improvement, pretty dramatic implications for building sort of robotic systems that can do more complicated things, because grasping is just a fundamental piece of what you might want a robot to be able to do in the broader sense. The other thing we've been focused on in robotics is how can we actually get robots to acquire new skills more flexibly than sort of hand coding exactly what they should do. And so on the left here, you see one of our AI residents in their daily work. No, they do many other things. They write great papers, but they also collect training videos for the robot to emulate. And you can see this simulated robot is trying to emulate the behavior it sees from the pixels of the video. And on the right-hand side, you see a few short video clips of people pouring into different kinds of cups or mugs. And then a robot that takes those 15 clips, 6 or 10 seconds long each, and with about 15 trials using reinforcement learning, trying to emulate the behavior it sees, pouring into a cup at a different configuration and so on, it can actually learn to pour, right? So normally, if you were trying to teach a robot to pour, in the old school robotics, you would hand code a control algorithm that would take you months and months to write and would be very brittle with respect to the orientation and the particular kind of cup that you're pouring into. Now we can actually have a robot learn to pour. It's not perfect. I would say it's like 4-year-old level, not 8-year-old level. But in 15 minutes, it can actually learn that behavior to pour. And that really means that robots can use data about the world and humans doing things to acquire new skills. Okay, advanced health informatics was another one of the grand challenges, and one that I'm particularly excited about for the potential of machine learning to really have a big impact. We've been doing work in this space for a while. One of the areas that's going to be impacted is various medical imaging problems. So let me give you one example of this, one that we've been working on for quite a while in our group now, which is the diagnosis of a disease called diabetic retinopathy. So this is the fastest growing cause of blindness in the world, and if you have diabetes, you should really be screened every year for signs of this disease. And there's 415 million people in the world with diabetes. And regular screening is really important because if you catch this disease in time, it's very treatable, but if you don't, you can suffer full or partial vision loss before you actually go get treatment. And in India, for example, there's a shortage of more than 100,000 eye doctors, and because there aren't enough ophthalmologists to screen these images, 45% of patients suffer vision loss before they're actually diagnosed. And the way it's diagnosed is essentially you get a retinal image of your fundus, the back of your eye, and then you assess that image on a 5-point scale, looking for little small hemorrhages like you see on the right-hand image here. But it turns out this can be modeled with just a general computer vision model trained to detect monkeys and cars and so on, and instead can be repurposed and trained on fundus imagery and trained to predict one of these 5 categories, 1, 2, 3, 4, or 5. And if you do that and you get about a couple 100,000 fundus images and you get them labeled by ophthalmologists, you can actually get a model that is on par or slightly better than the US board-certified ophthalmologist at this task. And that's pretty important because now we have a system that can actually take this assessment and do it in an automated fashion. You can actually do even better if you get the fundus imagery labeled by retinal specialists who are a subcategory of ophthalmologists who have much more training in retinal disease assessment. You can actually improve the model quality to be on par with retinal specialists, which is kind of the gold standard of care in this space, rather than just board-certified ophthalmologists. And so now you have a model that is the best kind of care possible that you can move around. and used all over the world. The other kind of interesting thing is by looking at fundus imagery, these models are able to detect things that ophthalmologists cannot detect. For example, we've been able to show that you can actually assess a bunch of factors that are all related to your cardiovascular health. And this was a complete surprise to ophthalmologists that, for example, you can assess the biological sex of the owner of the eye from the retinal image. They had no idea that this was even possible, but we're doing that with 97% accuracy, whereas an ophthalmologist would be 50-50 coin flip. And so we now have a new biomarker that can assess your cardiovascular health in a non-invasive way, just a retinal image, to the same level of accuracy that you normally need an invasive blood test and send the blood off to the lab, and 24 hours later you get the results back. So that's pretty exciting. The other kind of thing we can do is use decisions that have been made by doctors in treating lots of patients, recorded in electronic medical records, to help improve decision-making by doctors for other patients. So we've been working on essentially using machine learning techniques designed for sequential prediction problems and modeling electronic medical record data with the same kind of approach. So essentially, you can take an electronic medical record, line it all up on a timeline, group it by category, and then have a machine learning model go over this data one sort of event at a time, and then be able to make predictions of a bunch of different kinds of things. So for example, will this patient be admitted to the hospital given their current condition? What is their likely total medical expenses? Are they likely to develop diabetes in the next 12 months? What are the likely diagnoses for this patient given their current state plus their past medical history? And so to show that this might be possible, we collaborated with the University of Chicago, Stanford Healthcare Center, and University of California, San Francisco Medical System to publish a paper using de-identified medical records. So we have no identity information about the patients, but we've essentially got a large collection from each of these healthcare systems of de-identified medical records. And we can then train these sequential prediction models to see what we can do in terms of prediction. And what we show is that we're actually able to, for example, predict someone's mortality risk to the same level of accuracy 24 hours earlier than we would otherwise using the kind of current approaches for predicting mortality risk in healthcare systems. That really gives 24 hours earlier notice to physicians about which patients are critically ill and really need their medical attention. Okay, one of the vaguest of these grand challenges was engineer the tools of scientific discovery. One of the things we've been doing is if machine learning is going to be critical to deploying machine learning systems and training, doing machine learning research, and using it in all these different kinds of scenarios, we wanted to have tools available that would make that easier. And so TensorFlow is kind of the second generation system that we've built for our own internal research and deployments. And we decided to open source it when we started building it. And the first system was released in November 2015 with this flexible Apache 2.0 license, which basically means please take it and do whatever you want with it, pretty much. And it's been really nice to see a pretty vibrant community develop up around using TensorFlow, improving TensorFlow for a variety of different tasks. So TensorFlow is this purple line here. This is GitHub stars, which is one measure of interest in a particular open source package. And you can see it compared to a bunch of other open source machine learning packages. And it's really caused what we hoped would happen, which is this open source community to spring up and to work to improve the system, to use it for all kinds of different things. It's been downloaded 36 million times, which is a fair amount for a fairly obscure programming-related kind of tool. And people are doing interesting things. So there's a company in the Netherlands that, for example, is building fitness sensors for cows. And they can tell you which of your dairy herd is behaving a little strangely today using analysis of the sensor data with TensorFlow. There's a collaboration between Penn State University and the International Institute of Tropical Agriculture in Tanzania to do deep learning for cassava disease. So cassava is the third most important, largest source of carbohydrates in the world. being able to detect diseased plants by having a cell phone application that runs without any network connectivity. This is really an example of where machine learning really wants to run in lots and lots of environments in the world, including some where you don't necessarily have connectivity to the internet. You really need it to run on device in a way that can be power efficient on a phone. But you can take a picture of your plant, and it will tell you, is it diseased? If so, how you should treat it. One of the other things we've been focused on is how can we make machine learning easier? Because right now, the expertise to train machine learning models is actually fairly constrained. There aren't that many people who have got a lot of experience with this. So one of the things we'd like to be able to do is make this a lot easier for people. So currently, the way you solve a machine learning problem is you have someone with machine learning expertise, you have some data, you have some computational devices, you put all these together, the machine learning expert runs a bunch of experiments, and you store it all together, and you hopefully get a solution. We'd like to turn this into something where you need much less machine learning expertise, and you can replace a lot of that experimentation that a machine learning expert would have done with automated experimentation to come up with good solutions. And so can we turn this into data and computation giving us solutions? And one of the things we've been doing in this space is when you train a machine learning model, a deep learning model in particular, there's a lot of questions about what architecture structure should that model have. Should it be 7 layers or 9 layers? Should it be connected with 3x3 filters or 5x5? Should it use skip connections or dropout? And so neural architecture search is a way of automating this. Essentially, we have a meta model that proposes model architectures. We can then train those architectures. So we generate 10 of them, train those 10, see how well they work, use that as a feedback signal to the meta model to say, OK, these ones work pretty well, do more like that. These ones didn't work very well, you do less like that. And over time, you get more and more accurate models from this approach. And so, for example, AutoML in the ImageNet domain, which is a pretty difficult problem that a lot of people in the world have spent a lot of time on, this graph shows computational cost on the x-axis with accuracy on the y-axis. And each black dot here is some significant improvement in this space done by usually a team of machine learning experts or computer vision experts at some of the top institutions in the world. And if you apply AutoML to this problem, you actually do better. And really, that's because AutoML can do many more experiments than human supervised experiments in this space. And that's true both at the upper end, where you care most about accuracy and you're willing to pay whatever computational cost it is. But it's also true at the low end, where you might want a very lightweight model that runs on a cell phone in the middle of a cassava field. And we've done a lot of work in the space looking at using evolutionary algorithms rather than reinforcement learning, learning optimization update rules, incorporating both accuracy and the computational cost into the reward function. So you can say, I want the most accurate model that will run in 7 milliseconds, which can be important for things like autonomous vehicles or where you have a cell phone where you want a lightweight model, learning augmentation policies, exploring many architectures simultaneously to reduce the cost. So this is a pretty interesting area, I think, and one we'll continue to do research in. Finally, the other thing that's interesting is machine learning and the use of it is really changing the kinds of computers we want to build. And so we want more computational power, because every time we add more computational power to some of these problems, we seem to get better results. And deep learning is really transforming how we think about computers. So all the deep learning algorithms I've discussed have 2 really nice properties. So one is that reduced precision is OK. So if you carry things out to roughly 1 decimal digit of precision, that's perfectly fine. You don't need 6 or 12 decimal digits of precision. And also, they're all made up of a handful of specific operations, basically linear algebra kinds of operations, matrix multiplies, vector dot products. And so if you can build computers that are specialized for doing reduced precision linear algebra, that's a very specialized kind of computer, and you can actually get computational efficiencies because that computer only needs to do those things. So we've been doing this for a while. This is kind of the 3rd generation of specialized hardware we've built for this kind of problem. This is the Tensor Processing Unit version 3. One of these boards with 4 chips has 420 teraflops of compute, which is quite a lot. They're available through our cloud products, so we can actually access these externally as well. They're designed to be hooked together into fairly large configurations that deliver more than 100 petaflops in one pod. And we have many pods available for different kinds of work internally and externally. And they're programmed via TensorFlow. So the whole thing is designed so that you want these devices to be easy to program. So we have essentially an implementation of all the TensorFlow operations that runs on these devices. And so the same program will run on CPUs, GPUs, or TPUs. And the same program also scales with synchronous data parallelism without modification to go from one of these boards to one of these large pods. One of the things we're trying to do is bring more computation to the academic and research community. And so we've been making 1,000 of these TPUs available for free to researchers who have interesting ideas that would benefit from more computation. In particular, you have to be willing to openly publish the work that you've done with this, ideally open sourcing code, but that's not a requirement, but openly publishing the work that you do with these computational devices. And so actually for this audience, we'd like to make an offer available of a bunch of cloud TPUs that you can get. Here, I'll click there, take a picture now, so now you know how to get them. Where basically you can get access to some of these TPU devices for your own work, as long as you're willing to publish it openly. Okay, great. And you can also try it in your browser. So we have a Colab implementation that works directly in the browser. Okay, the final thing I'll talk about is thoughtful use of AI in society. I think as we've been using machine learning in more of our products, we've been thinking about how do we make sure that the way we do it is responsible. And in June last year, we published a set of principles that sort of crystallized our thinking around many of these areas. You can see the principles listed there. You can read them on the web. I think it was actually really important for us to do this internally so that we actually had sort of a clearly written set of principles by which we look at our own uses of machine learning. And we made them public because many other institutions are thinking about some of these issues, and perhaps we can sort of help participate in this conversation. I'll point out that many of these are sort of active areas of research. So if you look at number 2, for example, avoid creating or reinforcing unfair bias. A lot of these machine learning models are trained on the world as it is, not the world as we would necessarily like it to be. And techniques for automatically removing bias that we consider unfair are really important. But just to show you this is an active area of research, these are research papers we've published in the last few years on this topic. So this space is evolving, but it's a really important one. Okay, so finally, deep neural nets and machine learning are really helping make headway on some of the world's grand challenges. I talked to you about some of them. It's showing great promise in many other ones. You can find more about our work there, and an overview of our 2018 work is available on that blog post. And with that, I'll take a few questions, I guess. Thank you.
All right, thanks so much.
Sure.
So we have a few minutes, so we'll go through 3 questions or so. So the first one is a rather personal question. So, I mean, you've been in this for a long time. You were with Google since '99, right?
Yes.
So when was the first time when you had this moment, this sort of holy beep moment, when you realized that, okay, Google is going from a search company to be a machine learning AI company? I mean,
Right.
really understanding this is going to happen.
So we've actually been using machine learning for probably 15 or 16 years. So we've been training large logistic regression models for a variety of things. I think the time that I realized this was going to be really important was when we started to look at what could we do with training very large-scale neural networks. So I bumped into Andrew Ng in a micro kitchen at Google, who was spending a day a week at Google. And I said, oh, what are you up to? He's like, I'm not sure yet. But at Stanford, some of my students are training neural nets and starting to get interesting results. I'm like, oh, that's cool, because I remembered back to my 1990 senior thesis on training neural nets. And I said, why don't we train really, really big neural nets? So we put together a system that could actually train neural nets on thousands of computers simultaneously to really scale up. And we were starting to get really good results. And I was like, there's something here.
There's something here, yeah. Okay. And so, I mean, you invented map reuse, you invented big tables, so you basically invented the core technologies that made the big data world that
With collaborators.
With collaborators, okay. TensorFlow, you were at the forefront as well. So, I mean, if you're not touring the world and giving these relatively high-level talks, are you still, which tool is Jeff Dean building today?
Yeah, so I'm working hands-on on one particular project that I'm excited about, which is how can we build a machine learning system that really allows us to train models to do thousands or tens of thousands of tasks simultaneously, because we know that multitask and transfer learning work really well at the small scale. You know, usually you have like 3 or 4 tasks where you transfer learn from one thing to one other thing. But I have a suspicion that if we train a single model to do the thousands or tens of thousands of things that we're currently training separate models to do, we'll get great improvements and great benefits of being able to learn to do new tasks more quickly and with less data.
Okay. And the last question that was also posed from the audience is that shift from going to machine learning being very good at niche tasks to general machine learning, general AI. I'm not going to ask when is it going to happen, but is that something, I assume it's something you're actively thinking about and working on, and can you maybe give a few insights in that, where your thinking is there?
I mean, I think the reason machine learning models are good at narrow things and nothing else is we train them to do that one thing. So I think part of what the previous project I described is, can we train a machine learning model to do many, many things, and then be able to leverage that expertise in learning to do new things by saying, oh, this new task looks a lot like these other 7 or 8 tasks I already know how to do, but with some differences. So maybe I can do reinforcement learning or some experimentation to see how to solve the part of it that I don't know how to do, but really leverage the expertise that the system already has in doing other things to learn to do new things.
All right. Fantastic. Well, thanks again so much for being here.
Thank you.
Thank you.
All right.
And have a great day. We know you're going to stay at EPFL and meet with some students.
Yes.
So thanks very much for that.